welcome back. This is part 3 of Module 1, and this one's still about motion, but it's also about the motion of waves, just an introduction to waves. So we've been focused on forces up until now and how the different forces on an object play a role in that object's motion. So now we're going to be able to transition and look at this other type of motion. That's the motion of waves. Now when I say wave, what do you think of? Maybe little kids waving hello in your neighborhood, or the waves crashing on the beach, which is an example that we will be able to use. All right. This one is much more accurate than the saying hello version. All right, but what we're going to consider first are the mechanical and electromagnetic waves that are around us every day of our lives. All right. So let me ask this: have you ever held a rope and moved it up and down to create this type of ripple pattern? It might be something you've done in everyday life, maybe in a physical education class, just playing outside, or you might have seen more of a new fad with athletes doing these battle rope exercises. I've done them. It's very cool. They're called battle ropes or undulation ropes, and you're just making waves by moving your hands, with these ropes. It's pretty cool. So if you have seen this type of motion or created this type of motion with a rope, you have seen or created a wave, of course. And the definition of a wave is a disturbance that moves through space or a specific medium. Now, it's very general, mainly because many waves, like sound and light waves, they move through air, whereas some waves will move through a specific medium, like water, or through the rope seen above, or even the ground beneath our feet, which we will get into in later modules. But to keep it simple, think of waves as disturbances that move through space in different media. One other important note about waves is that they carry energy, and they can transfer that energy through the wave to other places. And thanks to this graphic from factmyth.com, there are these two main types of energy transporting waves. You have mechanical and electromagnetic. Mechanical are the ones that I mentioned require a medium to move through. Ripples in water from touching water, or waves in the rope we just saw, or even the sound waves through the air from a speaker right now or your headphones into your ear, right, to then vibrate your eardrum to signal the sound. Right. Now electromagnetic waves, right, they're a whole different ballgame here. These waves do not require a medium, and they can travel through the vacuum of space. Microwaves from heating your dinner, radio waves from a music streaming service, or the light waves from stars in the night sky. Okay, the sunlight is a great example of how waves can transport energy, right? So energy from the sun travels through space, through our atmosphere, and warms our planet and gives us light. And the sun's energy is so intense that this just came up in my own house. My thermostat in the house, the temperature controller, was jumping from 74 up to 84 in my house during the mid-afternoon. I was confused as to why. And then it would just drop back down. I was like, uh-oh, something's up with my AC unit. No. When we saw the sunlight coming through a small spot on our window in the afternoon light, and it was hitting the thermostat directly during this time, and the energy from those light waves was so intense that they caused the sensor to jump up 10 degrees, interpreting all that heat energy from the sun. Pretty crazy. So they can transport energy. These two types of waves are able to transport energy, and that's good to remember as we move through not only this part of the module, but in modules to come. Okay, so we've seen the two types of energy transporting type waves. If we come back to the mechanical version of these waves, like the movement through the rope, we can then define two main types of waves from there: longitudinal and transverse. And we see a look at those here. So longitudinal waves, or otherwise known as P waves, which stands for primary, all right, and that's because when we're talking about these two types of waves, primary waves are faster moving waves, and if you have both types of waves, P waves are going to reach their destination first, the primary waves. So notice that it's like a spring or an accordion, compression based. Something is pulled back and then released, and that starts the wave motion here. Okay. Now notice, the big thing here to note is that the motion of the wave is going in the same direction as the stimulus. Notice the stimulus pulled back and horizontally, in the horizontal plane, pulled back and released. All right. The wave also moves horizontally. Okay, this is different from the transverse wave or the S wave, also known as secondary waves because they're slower. Right? The motion of the wave here is perpendicular. All right, the motion of the wave is going horizontal. The stimulus was vertical. All right, so the hand was moved up and down to create this wave, and the wave then moves horizontally through the medium. So longitudinal direction of stimulus and wave motion are going in the same direction. All right, horizontally here. All right, again, these are called compression waves, and an example would be how sound can move through air. Okay, whereas transverse waves, the stimulus occurs on an axis that is transverse to the direction of the wave motion here. So stimulus perpendicular to motion of wave. So we have P waves, longitudinal waves, or we have S waves or transverse waves. Now I'm going to draw a wave here because when we talk about waves, a lot of different vocabulary comes up. Okay, so there we have a wave. It's best to use a transverse or an S wave here to go through the vocabulary. We're going to need to really get a deep understanding of how waves work. Okay, so here we have one cycle of this wave, right? It goes from a starting point through the bottom here, okay, back up to the top, all the way through this whole pulse, and back to the original, starting plane or the midpoint there. So a couple of terms come right up with what I just said. First of all, we have the distance from here to there. That's something called amplitude. Okay, and amplitude is the height of one portion of a wave, or you can say the magnitude of the wave. So here you have the upward height. You could also measure the down height here as well. It's going to be an equal amplitude there with this wave. Now the low point and high points we're speaking of, you have the high points. Those are going to be, and let me change my color here so things stand out. That's going to be our peak. So we have the peak of our waves. We also have the trough of the waves. That's the bottom point. So peak, high points, troughs, low point. So you'll see this as we have multiple waves added to this. We'll be able to actually look at some other vocabulary around peak to peak or trough to trough. We'll see that in a sec. So the next vocabulary point that comes up with waves is something called period. Okay, and period is how long for each cycle, or how many seconds there are for each cycle. So how many seconds per cycle. Okay, so I said that this wave over here, that's basically one cycle because it's going from that starting point back, through the trough, through the peak, and then back to the beginning, if you will. Okay, so how long does that take? How many seconds per cycle? That's period. And this is noted with the symbol T. Okay, so period will be seen as T. Okay, and if we take this a step further, right, we can look at the inverse of period, and that's something called frequency. Okay, and frequency is going to be how many cycles in 1 second. Okay, so the period, how many seconds per one of these cycles, and the frequency is, well, how many cycles could it go through within just that 1 second time frame. Okay, so the notation for frequency, and I'm going to inverse the colors here. All right, so frequency is seen as F, but I said it's the inverse, so we could also see it as 1 over T, couldn't we? Okay, so let's say, and again, let me change colors so we stay clear here. Let's say that the period here, it was 2 seconds. Okay, so the period of this wave, it was 2 seconds for it to go through one cycle. So then the frequency of that, well, it's the inverse, right? So if T equals 2, well, then the frequency must equal 1 over 2. right? So 1/2 of that. So there was 1/2 cycle within 1 second, right? And one unit you want to make sure you see is hertz. Okay, so hertz is cycles per second. Okay, hertz is also cycles per second, and cycles per second, of course, is how we measure frequency. So now you see the inverse relationship between period and frequency. If it takes 2 seconds for this wave to go from here to there, right, the frequency of that wave is going to be 0.5 hertz because it can only go 1/2 of a cycle within a 1 second time frame. All right, the frequency is always within that 1 second time frame. All right, so quick review. We have, one cycle here of a wave. All right, this is an S wave. It hits its peaks, it hits its troughs. The amplitude is the magnitude of this wave from the origin up to a peak or a trough, down to a trough, I should say. We have the period, how many seconds per cycle, and the inverse of that, how many cycles in 1 second. Okay, so we have some variables with waves that now deal with time. All right, but if we want to consider the speed or the velocity of a wave, right, and velocity is big with motion, right, we want to know velocity. How are we going to get that? Well, velocity, right, is what? It's equal to d over t, right? And we have the time thing taken care of, but the distance, well, we need something to talk about the distance of a wave, and that is where this idea of wavelength comes in. So wavelength, okay, which is represented with the Greek symbol lambda. It looks something like this. It's not the best. That's not my best drawing. But that's what wavelength is going to be. And that is the distance the wave traveled in 1 cycle. Or we could say 1 period, right? So that is from here. We marked it before with green. We're going to mark it again. How long what's the distance the wave traveled from here to here? Okay. And if we were to continue this wave, if we were to say the wave continued like that, and even down again, if we continue, we could say, from this peak to this peak. That's also considered wavelength, or this trough to this trough, right? It's the same distance as this origin to origin there. So wavelength is the distance traveled, okay, and we can mark that with a bracket here, okay, in 1 cycle or 1 period. All right, so now we have the distance part, right, of velocity. So we can come back to figure out, how do we determine the velocity of a wave? And this is just an intro to this concept. We're going to really need this when we get into later modules when we're connecting it to the Earth and earthquakes. Right? But for now, let's just think about breaking down the velocity equation and how we're going to frame this around a wave. Okay, so velocity of a wave, we can use the V. Velocity of a wave is going to equal the distance over the time. Well, what's the distance? It's, of course, our wavelength, right? And then over the time it took for 1 cycle. Well, that's the period. So if we divide this by the period, which we noted over there as t. Okay, so there we go. We have velocity of a wave is going to be equal to the wavelength, the distance 1 cycle traveled, over the time it took for that 1 cycle. So we have wavelength over time. We can rewrite this, all right, as wavelength times 1 over t, right? All right, because the same thing, multiplying the fraction of that, the inverse over t. And what did we say that 1 over t was? Well, that's equal to the frequency. It's the inverse thing. It's the same thing. Okay, so then we can even rewrite this further, and we can say that the velocity of a wave is equal to the wavelength times the frequency. All right, so V equals wavelength times frequency of the wave. So that is an equation we are going to need moving forward into other modules. All right, so for now, hopefully you have a just general understanding of some of the vocabulary around waves, the types of waves that exist, and now we see how we can look at the velocity of a wave. All right, So we'll take a different look at this and more of an applied look at this in the later modules. So quick review, a wave is a disturbance that's going to move through space or a specific medium. And these waves can carry energy, mainly mechanical and electromagnetic waves being those ones that do carry energy. And we'll look at the forms of energy that would be covered under these waves in the next module. All right, but for now, they can carry energy. And we have the difference between a P wave, longitudinal waves, having the same direction of stimulus and wave motion, versus S waves or transverse waves. The stimulus and the wave motion are going to be perpendicular. And we also have all this new vocabulary around waves and wave velocity with our new equation, velocity equals wavelength times frequency. And all of this last portion with all the different wave vocabulary was adapted from a Khan Academy video this is exactly framed around that, and has a lot of great other information to even make this more intuitive for you. So please, if you'd like to view that further, it's linked in the resource pages, and you can go ahead and extend your learning a little bit. And also in the resources pages, make sure you're accessing the practice documents to apply what you've gotten from this video to some practice problems and practice assessments. So that's it for this video. We'll see you in the next one.